I'm a PhD student. Oh, yes, you're going to do an intro, sorry.
Yeah, no, definitely. Yeah. So hi, everyone. Welcome to the 59th session of the MedAI Group Exchange Sessions. And this week we have Ethan Steinberg from Stanford here with us to speak about his work on representation learning for EHR using language modeling. So Ethan is a PhD student in computer science at Stanford University, and he's co-advised with Jure, Leskovec and Nigam, Shah. So he's interested in the intersection of machine learning and healthcare and how we can better use deep learning models to improve our healthcare system. So thanks so much, Ethan, for joining us today. And before we actually get started, do you have any preferences on how you'd like to take questions? Is it okay? Oh, sorry, go ahead.
Questions during the talk are perfect.
Okay, cool. So let's try to make this session as interactive as possible. And without further ado, let me hand it over to Ethan.
So as mentioned, I'm Ethan Steinberg, and I'm a PhD student co-advised by Nigam, Shah, and Leskovec. I'm here to talk about my research that I published, language models and effective representation learning technique for electronic healthcare record data, as well as some future work that was done on that, top of that. Before I start, I just want to thank everyone who contributed to this work listed as co-advisors. To begin, let's start with sort of an introduction for why we care about one of the reasons why we care about machine learning in healthcare. During the practice of medicine, one of the core clinical algorithms that doctors perform is sort of risk assessments in order to assign correct treatments. We have a whole list of potential treatments, medical treatments that have quite a few downsides and costs. That means we can't give them to everyone. So we try to assign them only to people who we believe are at high risk of some negative outcome. For instance, for people at high risk of heart attacks, we assign them statins. For people at high risk of cancer, we're going to give cancer screenings, diabetes likewise. As an aside, we're actually running one of these models, or Nigam's lab is actually running one of these models in Stanford Hospital right now to predict mortality risk to assign palliative care. But as for most of these things, it's only worth giving the treatment if the risk is high enough. Currently, most of these risk calculations are done sort of in an ad hoc manner through physicians manually trying to determine whether they think this patient has a particular risk or not, or through simple calculators or other sets of guidelines. There's actually some really fun papers that actually try to estimate the AURC of physician risk prediction. But the premise of machine learning here is we can, in theory, predict these risks much more accurately with machine learning, with using actual computational techniques than either manual predictions or just the current standard rough guidelines. So how do we actually build these risk models? To start, we just want to give an introduction to the data we use for it, which is the EHR. So EHR stands for electronic health record. It's basically a patient timeline of all the information that we have medically on a particular patient. We have a bunch of events, they're all time-stamped, and they come from a wide variety of sources. So here's a diagram just showing the data that we used, or the types of data that we used in this study, which was the diagnoses, which are the doctors write down the patient has a condition, procedures, when the doctor orders a procedure, does a procedure on a patient, like a surgery, lab tests, you order lab, like a HbA1c or something of that nature, and also medications, where the patient is given medications. I just want to note there's a lot of other data that's also in EHRs, such as images and notes and all sorts of other weird data types, but we didn't focus on that for IRB and related reasons. So what do we actually do with these EHR records? We construct these risk algorithms or risk prediction setups. You do that by defining a prediction time, for instance, in this case, September 3rd, 2020, and try to use all data from the past to predict risk of future events past that time. And it's very important to ensure that you don't have any leakage from the future to the past or anything of that nature. So there's sort of two main types of challenges for trying to build risk prediction models with EHR data. The first category is that the first category of problems is the data type is sort of confused or sort of weird. EHR data is this weird nested temporal structure. For every patient, you have a series of visits. Within each visit, there's a series of events, which are these IC codes or lab tests or other things. EHR data is also very sparse. There are thousands upon thousands of potential ICD codes. Each patient will only be annotated on a couple dates. Similarly, for lab tests, there's hundreds, if not thousands, of lab tests that Stanford regularly does, but each patient will personally only see a very small number of lab tests. It's also our data for developing these risk models is also very limited due to two primary reasons. First, we're limited to single sites, mainly due to legal IRB reasons. And second, we often care most about rare events. Like most of the risk models we care about are for stuff like mortality or heart attack or stroke, things that are rare by their very nature. And so you're not going to get many positive examples of those events in our data natively. The classic technique, or at least well, not really classic, but the modern technique for trying to build these risk models is to sort of direct deep learning, where you design a neural network exactly for the data at hand. So basically, you'll have some sort of recurrent layer to deal with the nested temporal structure. You'll deal with the sparseness, so things like embedding, stuff like that. And the sort of like learner representation implicitly as it trains, and it directly handles the data as it is. And this, in theory, lets you capture all the signal from like that nested temporal structure and all the other things. Because in theory, it's processing the raw data. So in theory, it has computational power to process everything. However, most like benchmarks that try to actually evaluate like a wide suite of methods find that this doesn't work very well. Hierarchical and China are probably the two best examples of this, where they did like sort of wide evaluation of a bunch of different techniques. I guess, well, at least my current theory, and one some other people believe, that there's simply not enough data for direct deep learning to learn these risk models, mainly because we have such a limited amount of data and generally a very small number of positive examples. So the point of this paper is sort of to explore transfer learning as a potential solution. The idea behind transfer learning is we have a large unlabeled data set, and we're going to try to transfer information to a small labeled task data set through various techniques. And sort of the fundamental assumption here is that there's an assumed shared underlying structure between these two data sets, so that even though they might not overlap exactly, there's something you can learn from a labeled data set that is still applicable to the small labeled task data set. And because the large and labeled data set is so large, you have much more data to learn that shared structure. So this is currently sort of the state of art in NLP, which is currently really using transfer learning to achieve very good results on a bunch of tasks. Basically, they're large data sets, usually a large collection of English text, such as Wikipedia or book corpus, and they'll use something like BERT to transfer it to like a sentiment analysis task, where the shared structure behind the two is the sort of shared English structure, as it's all like English sentences, and it's all follows English grammar, etc. So the idea here is we should be able to do the same thing with EHRs. We have an entire patient population to learn from, and we can in theory transfer that information to our small like inpatient mortality tasks or other example tasks. Just to give an example, like for example, we have, I think I have the numbers later on, but something around a couple thousand inpatient mortality deaths recorded here at Stanford, but we have like 3 million EHR records. So it's a huge size difference. And the assumption, of course, is sort of like the shared medical like reality here, in that like we might only have a couple thousand patients who die. We have a bunch of patients who get like put in ICU or something like that. There's probably a shared underlying like risk structure there for the covariates in terms of what causes a patient to die and what causes a patient to have other outcomes. So the current state of the art for NLP is sort of these like language model-based representation learning approaches. BERT, fit, ELMO, GPT-3, etc. The basic idea is we have this what we call like a language model, which is a model that predicts the probability of the sequence, as in it's like sort of like a generative model. And the idea is we can learn a language model on our unstructured data, and then we fine tune on our small data set. So it's useful here to like sort of discuss how this like for exactly how it works for English. So for English, we have this like sentence: the quick brown fox jumps over the lazy dog. And like an English language model try to predict the probability of that sequence, the probability of seeing that sequence of words in a piece of text. The key insight here is that it's a similar sort of like, we can sort of think about the EHR as like a similar language, but it's a language in terms of like ICD codes and like other coded information. So for like the EHR language, you have like a visit with a certain ICD code and a CPT code, followed by another visit where they pick up aspirin, followed by some other visits. And the idea is we can, in theory, construct an EHR language model that does the same thing, that predicts the probability of that sequence of visits, that sequence of coded event information. and then apply the same technique as before, where you fine tune it on some target task of interest. So how do we actually construct this? How do we actually construct a model that computes the probability of an EHR record? There's two main components of this that are sort of analogous to the components of a text language model. First, we have to have like an encoder that takes our raw data, takes our EHR like raw data records, and computes sort of like an intermediate representation. And then we have a decoder that takes the intermediate representation and computes the probability of the entire sequence. So for the encoder, for this paper, we use pretty much the standard model, or at least the most common model for processing EHR records with deep learning, which is a sort of like GRU combined with an embedding approach. You handle the sparsity of our data by embedding all the codes into an embedding space. And then you take the mean of the embeddings for all the codes in a particular visit or a particular day. And then you can handle the time aspect, and that sort of handles the nested, like temporal aspect of multiple codes within a day. And then you feed it into a GRU that will then take that sequence of embedding DAGs, that sequence of mean embeddings, and it'll output a hidden representation, hidden state for each day. That's sort of like this fixed length representation for each day. One important note is you also have to concatenate some time delta features for each of the coded data to give them all information about time. That information of this code appeared at this particular time in the record. For time features, we simply add both the absolute time as an absolute age of the patient, as well as the deltas, like the delta from the prior day. The assumption there is that both are important, but they give different information.
Ethan, can I ask a quick question here?
Yes.
So in your, like you mentioned, there are 4 different types of like visits, medications, and maybe ICD-9 codes that you're actually using for your patients. Mm-hmm. So like on a day-to-day basis, like maybe a diagnosis might remain the same for 3 days, but then the medications might change over the 3 days. So do you actually concatenate all of them, or do you still do the pooling across all these different types of data, or can you tell us a little bit more on how you handle this?
So for the EHR, we don't really, for at least for this model, we're only taking, for all the events, we only take the time it was started, the time the diagnosis code was like put on the record, or the time medication was started. We're currently not using any of the end event times.
I see.
So the code will only appear once.
Oh, I see. Okay.
But yeah, all the codes are combined into one embedding DAG and all treated similarly. So an IC code, if you have like an IC code and a CPT code, they'll both get fed in the same embedding DAG. Well, it means they'll have different embeddings for the different codes, but they'll go into the same average result.
I see. And so the codes 1 to N that you have mentioned, they encompass all like ICD-9 codes as well as medication codes, procedure codes, everything together?
Yes.
Got it. Okay.
May I know how big is this, like the dictionary, or like how 1 to N? How big is this N here?
The dictionary is about, I think it's somewhere around 30,000 or so. I think it's between like 30 and 100,000. I forget the exact numbers. It also depends which version of the data you run on. It's somewhere in that order of magnitude.
So would you have this problem when you like when you want to apply this trend model to a different institution? Let's say if one institution uses ICD-9 and then the other one uses ICD-10, how would you address this discrepancy here?
There's a couple approaches you could take. So the model itself will not work, but one thing you could do is you could do ICD-9, ICD-10 mappings, try to map your data. Well, you could do it in multiple directions. You could try to map all your different data sets to the same code standard.
Mm-hmm.
Alternatively, you could try joint training where you train the model on both ICD-9 and ICD-10 codes, like for multiple institutions at the same time.
Right.
But you're right, that is an issue. Like, although I don't think that's generally not even the small. Like, there's a ton of transferring from one institution to another is very complicated.
Mm-hmm.
I don't know. I've not done any experiments with that. I don't know if anyone has, because there's a lot of issues there.
Right. Got it. Thanks.
The bigger issue I think you'd run into is more that different institutions will have different coding practices. So even if you could match the codes exactly, you're going to get weird artifacts due to different like practices in terms of like just the practice of care and how they interact with the healthcare record.
Yeah.
Like
Yeah,
one thing
just
that's sort
curious.
of, I was
Sorry.
gonna say just like one thing that's sort of odd about Stanford data, at least odd in terms of how, well, I guess not really that odd, is that we treat like, we have like this whole, at least I think is like for our lab, all our lab codes are duplicated because of the order and the way the result. Some EHRs and some ETLs don't do that or do that differently.
Can you explain a little bit more about the time delta features also? I'm just curious how that works.
This is the simple possible featurization. You take the age, you take the delta, and you feed them in as long. You normalize them and then feed in those normalized features. There's also Encoder also log encoded, so the log time or so the log age and log delta also normalized added on. I'm not sure exactly which parts of the time features are important. I didn't run any inflation experiments. I just added everything and called it a day.
I see. So you look at a patient's timeline like for a particular day, and then you look at all the events that are logged, and then you take the corresponding time and you just put it as a sequence, like all the deltas, you just concatenate it as a sequence. Is that correct? Yeah. Okay.
Or concatenate to the sequence of codes. So you have the codes for that day. So that day had like 5 codes. You take those 5 codes, embed them, average those, and then concatenate concatenate the time deltas for that day. I
see. So you do not actually, do you also do an embedding for the time deltas, or do you just directly feed in the time deltas?
Directly feed them in. They are normalized those to avoid lots of various issues.
Gotcha. Okay. Thank you. And what's the embedding dimension? Like, just out of curiosity.
That was one of the, I think the optimal embedding dimension was like 800. I think I tried a couple options, 400, 800. The full list of high parameter grids in the paper, as well as the optimal for each setup.
Gotcha. Thank you.
And this is, I just want to, this is a pretty standard model. This is like what most people are, or generally do, at least most of the papers sort of do this type of model. This is nothing special about this. So next is our decoder, like how do we actually compute the probability of a sequence of codes, x1 through xn, where xi is a set of codes particular day. We use an autoregressive formulation. So the probability of a code equals the probability, so probability of a day equals the probability of that day given all prior days. And then you just need to define that probability of a day given all prior days. One interesting question is why autoregressive? There's multiple other ways you can do that probability of sequence. And in fact, the current top NLP models, or at least most, like BERT example, do not use autoregressive formulation, do not use an autoregressive formulation. There's sort of this theory here that autoregressive is probably more important for EHR data, mainly because when we apply these, we only apply them in the past. So we need to have models that only deal with past data to predict future. Although I run those experiments, but someone should run those experiments actually doing the full relation between autoregressive and the other types of objectives. So then how do we define that single data decoder? So how do we pick the probability of that set of codes given the prior history? It's a set prediction problem because you're trying to predict what set is going to be there. You can't directly model each set because it's sort of exponential to the power n because of n codes within that day. The standard technique here is binary relevance. At least the more common, at least the prior use technique was binary relevance for some of the prior work that did this EHR language modeling. Basically, you compute the probability of that set by taking the product of each code in that set. The main issue is it's expensive. It's O of M for the number of codes in the day. It's also, there's no shared parameters. You have to independently predict every single code independently. One important note here is that this is, well, actually I'll go into that later. So one thing that we do in our paper that's sort of new is we introduce a hierarchical decoder.
Ethan, can I ask a quick question about your previous slide? Sorry.
Yes.
So this assumption about independence of different codes, isn't that a pretty strong assumption given that there are like correlations between, let's say, medications versus ICD-9 codes and things like that? How do you get around with it? Or
it's a strong assumption. Well, so there's two parts to this. First, it's weaker than you think because it's a conditional assumption. It's probably that code given all prior medical history.
I see. Okay.
But it is still, even with that weakness, that weakness, it is still pretty strong. The more important part is that it's not strictly necessary to be correct it doesn't strictly need to be correct. In the sense that because we're caring about, we care primarily about our end goal target performance, we care about mortality models. Having a slightly incorrect language model is not the end of the world.
I see. That makes sense. Thank you.
Yeah, but there's some interesting ideas here. Like maybe we should do. Yeah. Well, we do something different here. That so also we have our hierarchical approach that's a little better than the independent assumption. Basically, we assume each code belongs to a hierarchy, and now you can compute these probabilities instead of. And now you can compute these probabilities hierarchically. For instance, skin cancer and lung cancer, consider those codes. We know that there's this hierarchy of codes. Well, this is obviously a hierarchy, but you can use any hierarchy. We can define these probabilities conditionally. So probability of skin cancer equals probability of cancer times probability of skin cancer given cancer. For our work, we use the IC10 hierarchy, but in theory, any could work. Oops. So why do you do this? It's more efficient, it's log n. It's also better accuracy through weight sharing. In particular, the idea here is because the probability, I guess I'll go back one slide. Because you have the shared parameter here, probability of cancer, that means you don't need as good of a model for probability of skin cancer, assuming that there's some shared structure between lung and skin cancer. And you can see that directly if you run predicting new diagnosis code experiments. This is a completely separate setup where you just try to train a model to predict new diagnosis codes. We do the ablation of hierarchical versus standard decoder and measuring the average prediction score of the binary relevance versus hierarchical decoder. Another note here is going back to that independence assumption. The independence assumption here is also a little bit weaker technically because now it's now independent given parents, but that's sort of a side issue. I'm not sure. I don't think that's that important. So now we've synthesized these down. So now we just need to find these conditional probabilities. The probability of skin cancer given cancer. We do that just by doing a dot product between the day embedding when you get out from that GRU, and then also the embedding of that skin cancer code. One neat trick here we can do is we can tie the encoder and decoder embeddings together to save memory. So the same embedding bag that's used here, we can use the same embeddings for our decoder. So now we define the full model. So now we have a full model that goes straight from the records to this representation, to these probabilities of the sequence. Now you just need to train it. You just use for training, you just use the negative log loss, try to optimize the entropy of the language model. So using the standard atom optimizer with a warm-up and decay. Learning rates get set up. You mainly need the complicated learning rate setup because it's sort of these are GRU models, and those tend to be unstable at the very beginning of training. And there's a whole grid for parameters for all the various different sizes of the layers, the weights, the regularization, all that stuff. We just run a grid over every possible option using the training objective as the objective. So how do we actually use these things? We find the most effective approach is just the simplest actually. You take the final layer and you feed into logistic regression models. The other approach, which you see more in NLP, is more fine-tuning, where you fine-tune the entire model into it instead of just the final layer. We find it overfits very, very quickly in our setup. Probably out of future work, because that's sort of the NLP find that fine-tuning works better, but we just didn't. And we're calling these climate representations for clinical language model-based representation, because we're building this probability sequence for the language model, and we're extracting these representations from that sequence model. So how well do these actually do? So we run a bunch of experiments on 5 clinical tasks. We use Stanford data from 1990 to 2018. We have a time split setup. So our training, test, and validation set splits are all based on years. So we train on the years, I think it was 1990 to 2016. We validate on 2016, 2017, and we test on 2017, 2018. So the same patient will show up multiple times, or in both the training and validation and test set, but it'll be different time points for that patient. So that's how you ensure there's no overlap between training and testing. For all representation learning methods, we only train them on the training sets to avoid any leakage from the future. There's about 3 million patients in our Stanford data set. With the exact counts, I forget the exact count, but yeah, around 3 million. We only use the demographics, diagnostics, procedures, medication orders, and lab test orders. These are your primary coded data sets, or coded features. Each one of these items has a code. So diagnosis of IC codes, procedures have CPT codes, medications orders have RX norm codes, and lab test orders have link codes. The coded structure is important because we're relying on that coded structure in our decoder. For the hierarchical decoder, we needed some sort of vacuum ontology. And that's why we use only those, well, that's primarily why we only use those features. We construct an experimental grid comparing a bunch of representations with 2 downstream models and a bunch of tasks. We also evaluate, sort of not on here because it's awkward, like an end-to-end experiment where you take the same architecture we use for a language model and you do end-to-end predictions. So we pick directly predicting the target task with no pre-training whatsoever. We evaluate 4 types of representations: counts, where you simply count the number of times the code appeared in the past, sometimes using time binning, where you like say, how many times did the code appear in the last month, 6 months, etc. LSI, latent semantic indexing, which is sort of like a PCA sort of approach on the count matrix to sort of compense it. Word2vec, where you take the sequential codes and you sort of flatten them, and then you train a Word2vec model on those. And then we have our language model-based representations. We evaluate 2 downstream tasks, or 2 downstream clinical model types: logistic regression and graded of trees. The logistic regression is regularized through L2, and graded of tree is likewise regularized through its special mechanisms. Graded of trees are chosen because they're sort of the mainstay for these sorts of risk prediction tasks. And then we have 5 tasks we look at: mortality, long admission, ICU transfer, readmission, and HbA1c. Well, it's actually abnormal HbA1c. For our patient mortality, the task setup is for a patient that's currently in the hospital, what is the risk of dying? Or sorry, for a patient that just got admitted, what's the risk of dying the remainder of the stay? Long admission is for a patient that just got admitted, what's the chance of having a stay greater than 7 days? ICU transfer is for a patient that's currently in the hospital every single day. What's the chance of being transferred to ICU tomorrow? 30-day remission. On discharge, what's the probability of being readmitted? And then abnormal HbA1c, which is before a patient takes the HbA1c as a blood sugar test. And this is before a patient takes a blood sugar test. What's the chance of them getting an abnormal result, so greater than 7, indicating they're diabetic, excluding all patients who already are diabetic from that cohort.
Quick question about the task setup here. So for mortality, long admission, do you treat it as multiple one-class classification problems, or do you is it a regression? Like, do you say, okay, how many days is it? Like, what exactly are you predicting in these tasks?
These are all binary classification problems. So yes, no, did the patient die long admission, or yes, no, did the patient have long admission?
Oh, I see. Gotcha. Okay, thank you.
Yeah, and one thing to note is that, as I mentioned earlier, like the same patient shows up multiple times, mainly if they're the frequent flyers and they get admitted multiple times. And so we also have reports number of unique patients as well as separately.
Got it.
So we run a giant hyperparameter search grid. So for every representation is, so we have like representation tuning, we have end model tuning, also running independently, with a bunch of different options for Word2vec and LSI and Climber, as well as the counts models. And so this reports the optimal performance, and all tuning is on like validation set, and this reports the optimal performance on the final set relative to the counts representation. We also report our confidence intervals, plus or minus 95%, based on test set derived confidence intervals. The reason why we report things relative is because it significantly reduces the amount of noise you get in your confidence interval, because it's highly because results are highly correlated. If you have a patient that's really hard, like a really hard patient, all the models are going to be correlated on that hard patient. And so by doing a relative measurement, you get much more precise measurements. And as we can see, sort of the count models do pretty well. We reproduce the ability for the count models to sort of outperform the end-to-end GRU, with one exception of ICU transfer, mainly because ICU transfer has the most data and it's the largest of our tasks. And then we see that Climber basically outperforms the count model in every setup. And in a statistically significant way, all this one's it's pretty close. We also want to compare it to a prior. So our main new thing we do in our language model is that hierarchical decoder. We also compare to a prior language model that didn't use that hierarchical decoder, but had the same encoder. We can show that the hierarchical decoder, even this is like multiple steps removed, right? This is like hierarchical decoder is not even being used for these sorts of applications directly because it's not being used past the representation stage. But we can see that just that itself improves the characteristics of the representations that we learn.
Sorry, could you remind us what's the difference between Climber and Dr. AI language model?
The Dr. AI language model uses a binary relevance decoder, so it predicts each output code independently.
All right, I see.
Where the Climber language model has that like hierarchical thing where it predicts it down that tree.
Makes sense. Thanks.
So we would expect representation learning to have the best results in low data settings. So we explicitly set up a sort of like ablation to test that by doing subsample experiments. So we constructed mini training sets of different numbers of labels. Note that we fixed the prevalence to try to avoid issues where because our tasks, a lot of our tasks are really rare, so you have to fix the prevalence like 10%, otherwise things will blow up. We also measure the statistical significance by doing test set confidence intervals, 95%, as shown on the little lines over there. We report four different representations as well as an optimal, the Oracle, which is like the Climber with all data. So we take the representation and then we train it on the entire data set. Oh, sorry, we take it on the entire patient mortality data set. And as we would expect, the representations have more of an impact at lower data set, at lower sample counts, especially once you get to 100 labels, then the effective expectation is quite large. We can also see that some tasks perform very differently from others. ICU transfer in particular seems to do very well with that representation, and where some other tasks don't do quite as well at low sample counts. And that probably reflects how far those tasks are from our overall our language modeling task. So there are two main conclusions here. So clinical language model-based embeddings perform quite well. And then we have especially large benefits at small sample sizes. So if you're running a very even smaller set, because before the task that we chose, I just want to emphasize, these would be considered pretty large tasks by most standards, even though they are smaller than might see in standard neural network stuff, like inpatient mortality and like long admission, those are stuff that actually happens to people in the hospital. There's some other things like for example, heart attack and other stuff that might be more rare. So that's basically the summary of this paper. Any questions about this paper first before I move on to some, I guess, work that was built on top of this?
I have a quick question. So this is pretty cool. Did you happen to also do like a disease subclass, or basically like how do these tasks like what are the numbers on these tasks for like different diseases to know like which diseases are, they perform really well on and which subclasses they don't perform well on?
We did not do any subgroup analysis. Yeah, we just looked at the overall aggregate numbers.
Got it. Okay, thanks.
Crystal, I have one quick question. It's Iman here. I just wanted to ask you that we work with Climber because we work with JSON, but we are facing a huge problem because you depend on the Stanford data structure. What is your plan of extending Climber for the more standardized data structure like OMAP or some FIRE or something like that?
The current version of Climber, at least the one that we have on our GitHub, is built on OMAP. So in theory, it does. We actually have run it on some of the future work on that I'm talking about was actually done on non-Stanford data because it's relying on that OMAP translation layer.
Okay. Okay. So you already have that model available, right?
Yeah. Although there's issues. I mean, there's some other issues. The main issue is that if you're using a data set that's coded differently, in terms of like it's not using any of the ontologies that Stanford uses, things will sort of break down because the ontologies have to be sort of manually handled.
Right. Okay.
Do you experiment with like transformer-based model like BERT or BioBERT?
We did some experiments with the transformer. We didn't find it really improved any much, and so we didn't do too much further with that. Well, there's sort of two aspects here that makes it different from BERT. One is the transform. One is that BERT uses a mass language model. And we unfortunately didn't really do experiments with either, so we don't know whether either of those. Well, we did some with the transform. The transform didn't seem to do much, but we didn't run any experiments with the mass language model yet. It is possible that transformer could result in improved performance. I'm just not sure.
I see. Thanks.
So move on. So one thing, well, I guess we're currently in revisions for this one, is how well can we use this to do causal inference sort of setups? So to evaluate this, we pull clinical trials, clinicaltrials.gov, and then we need to run observational studies to reproduce the effects and measure how accurate the reductions are. And this is one of Nigam's lab's other focuses, which are like causal inference stuff. So this work was done, not really related to Climber, but we use this as, while we're doing this work, we use Climber as a test bed. And so, well, because we already have a data set, we sort of ran through, we could see that if you compare the count-based propensity scores to the Climber-based propensity scores, you get substantially better precision of reproducing these effects at a fixed recall. 30% recall is just arbitrary number. So this was a pretty straightforward obligation. This is given the existing Climber model, given the existing representations, can we produce effects? And as noted, I'll just side note, this is done on Optum data, not Stanford data, mainly because in order to do any sort of causal inference, you really want to use claims data for a variety of reasons. And that was relying on that OMOP conversion layer. So now in terms of actual methods work, my current methods focus is trying to extend Climber to time to event modeling. So time to event modeling is really useful in healthcare, basically because we have censoring, we also have importance of time. By censoring, I mean that, let's say you're trying to build a risk model to predict heart attack. For a lot of our patients, we don't actually know if they ever develop a heart attack because we lose track of them. They either leave Stanford or they don't come, or they don't show up for whatever reason. And if you don't have a time to event modeling set up, you can't really handle those patients properly. You get a really biased estimate. And this is actually especially important for like patients with like socioeconomic discrepancies. Because those patients are more likely to be dropped out. And if you don't adjust them properly, you'll underreport their risk and underprovide treatment. And also, of course, the importance of time. Time event models are useful for healthcare in particular because we care about when an event will happen. A patient that'll get a heart attack in 1 year is very, very different from a patient that'll get a heart attack in 10 years. And so how you want to clinically treat them is very different. The main issue with these models, and the reason why they're not really used that frequently, is they're extremely parameter intensive, or much more parameter intensive than our standard binary risk models. Mainly because you have to estimate over an entire time horizon. Instead of just the risk of events within the next 5 years, you have to compute that risk continuously until your end of horizon, whatever that is. And just as an illustration, that figure on the right is just what like an example time event model might look like for a couple patients. That's totally fake, just what I did. So one question here is, can we modify Climber so it can work especially well in the setup, especially because this is an exact low data setting where we do need that sort of benefit. So we modify the pre-training objective. So instead of predicting the sequence, or instead of predicting the probability of the days at each time point, or the probability of predicting the next day at each time point, it predicts like the survival curve at each time point. So try to predict all the future survival curve, all the future time to event curves for every IC code. And then you can use this to extract representations and fine-tune those representations in a variety of standard survival models. And we can run these on 5 tasks, or 5 time to event tasks. And so we evaluated both this time to event Climber with that pre-training objective switch, as well as the baseline, as well as your pretty much standard data, which is like a survival forest.
May I know what's the loss function you use to train the model? Because I know like people use all kinds of different losses for time to event prediction. So
we used the standard log loss, the probability of the data given the model.
I see. So it's is it like the so are you predicting the time to events as like a regression problem?
Yes.
Okay, I see.
Yes.
So, but I don't see why this is more parameter than the binary classification.
Because you have to model, you're modeling not only the time, you're trying to compute these probabilities, you have to compute these probabilities over the whole time horizon, which is intrinsically going to be more parameters to estimate. Like this is like, it's not just your regression, it's also regression. You need like the error bounds. Like if you're going to use one of our baselines is one of our things is using a log neural model. like if you're going to train a log normal, you not only have to fix the mean, but you also have to predict like the variance.
Oh, I see. Okay.
And also, it's not unlike the binary model. We also want to do like piecewise models as well, which adds even more parameters, because the assumption is that like you don't want a single log normal for a time to event distribution is generally not good enough. So you generally want multiple log normals sort of stacked together in order to actually fit the time horizon.
Okay, got it. Thanks.
And so here in the survival forest, are you using still like time-based featureization, or you're just using one-hot encoding? Because the performance seems really low here.
Yeah, it's the count-based representation. We also have, I didn't include those, but there's also, this is the count-based representation over a bunch of different types of count-based representations. Yeah, it is the count-based representation.
Okay, so no time temporal component was involved. It's just count, right?
There is temporal component in the sense that you do have like one of the hyperparameters is for that count-based representation. Do you do multiple time buckets? So like one for like you have different columns for like a code within the last year versus code in the last 6 months.
Okay, so you are doing that like temporal, or it just count for the overall time period?
Well, it's a count representation that takes into account time. It's in the hyperparameter list, but it's not chosen because it actually turns out the time is not as important as my think. Or at least the cost of additional parameters is not worth the potential benefit, at least in our experiments. Like if you're interested, it's actually sort of interesting. If you go to the paper and you go, actually, let me just pull this up. Let me pull up that particular table that might answer some of the questions. At least for Climber, not for the, I don't have the survival stuff, but at least for Climber. Wait 1 second. So for the Climber paper, you can see here that so this is the table appendix E that reports the best like hyperparameters for each representation. And that's what this with time bin hyperparameter does, is it informs you that the time binning setup was the optimal hyperparameter for that setup. Although do note that actually this hyperparameter is not frequently, I think it's chosen for, well, it's chosen for 3 of the 4. It's not chosen all the time.
Okay, thanks.
Any other questions? Oh, I guess so. Your current questions, future work is, so the main data sets this is not using are the text and images that are available in the EHRs. Since this work was really started, the text and images have become actually a lot more easy to work with here at Stanford and elsewhere due to better data identification techniques. So there's an interesting question of how we can incorporate those to provide additional benefits. There's also that transfer site question. Can we transfer a language model into one site to another site? This would in theory allow you to access a lot more data and achieve a lot of other interesting benefits. For instance, there's a theory that like using a language model, you could transfer N models. Like if you train a language model on a shared language model, then you could transfer like a mortality model from one site to another site more easily. Those are just theoretical at this point. And that's it for all of my slides. So, any other questions or comments or feedback?
Awesome. Thanks, Ethan. That was a great talk. I guess before we move on to questions, we can all give a round of virtual applause to Ethan. Great. Yeah, and let's open the floor up for questions. I can actually get started with one. So EHR in general has like a lot of like missing data problems. I was wondering if that's something that you explicitly model or try to account for during your Climber language modeling process, or do you just assume that like if some entry doesn't exist, you just like avoid using that entry?
There's no real way we can model that. Yes, it's currently not modeled. Yeah, it's not modeled. That's all I can say. Is yeah, in general, the timed event work, that when you actually do model missingness, that when you do actually try to incorporate the fact that the patient's timeline gets cut off at a certain point. But it's not really modeled. You're not really modeling missingness. You're just making sure the model is aware to try and avoid predictions past that point.
I see. Would it be possible to include like so you have P of xi given x1, x2, so on, like you have a list of like previous events. I was wondering if like you can just have an additional code for a missing data thing and then just explicitly model that as well.
I guess the question is there, like, how would you, like, why would you insert that missing data code?
So I guess by not explicitly addressing it, like your model is now assuming that, okay, it just has data for XYZ, and then this like the missing value is something that the patient doesn't have. But versus a patient who has XYZ values, but also has an additional parameter that they might have like that. I'm just trying to see if that could be a potential cause of like differences.
Well, the main issue is that we don't actually know when data is missing. Like if we had some sort of signal in the EHR record, well, actually there are some. No, our data set does not have signals of missing data, but some data sets that do have missing data signals, and that would be a good thing to add to those data sets. Just that it's not available in Stanford data.
Oh, I see. Okay.
For instance, the claims data sets, Optum and Truven, do have missing data signals, and for that, you would actually probably want to do what you're mentioning. That is a good comment. For those data sets, you should. Which is, yeah, like I said, we ran our code on the Optum data set, but it would have been better if we actually took advantage of the additional data, like that missing data indicator that Optum has, which we didn't.
Got it. Okay. Any other questions for Ethan?
Yeah, so for example, the Stanford is a kind of like a care hospital. So many patients have like previous like 1 or 2 visit maximum in that hospital, you know. So probably you will not have like complete history of the patient. So how do you like suggest user to deal with those patients? Should we like drop those patients from the Climber usage at all, or we can include those patients, but the model will be a little bit biased towards those like patient who doesn't have a lot of visits like other patients?
So those patients are tricky. There's no real reason to drop them from training because they're pretty cheap to train on because they're pretty short. But you're right that 3 million number can be misleading because a lot of those patients don't have a lot of data. There's a sort of separate question there, which is like, so there's 2 questions here. One is like, what do you do with those short patients during like your model training? And there's a separate question, what do you do with those short patients during actual clinical deployment? I cannot answer the second question. That's a complicated question for actual physicians. But for us, we include them. We just don't get much signal out of them. There's no reason to throw them away.
Okay.
One additional question. So do you think Climber representations can be used to get similar patients in like in some format? Like do you measure similarity between representations for patients, and is there some future work that is being planned in that line?
We did some preliminary experiments for that got very bad results. It probably reflects just the problem is similar there is very ambiguous. Similar according to what metric is very tricky. Here's what we did do. We did clustering experiments and tried to see how well those clusters match like disease groups. Did not get anything of value out of that.
Interesting. Okay. And these clustering objectives, you just like, was it just like regular k-means or like standard clustering algorithms, or did you have to specify a different distance metric in order to actually make this clustering work?
We tried a couple of distance metrics as well. I think we tried L2 distance as well as cosine distance. Neither of them seem to do that very well.
I see. Okay.
I think one issue, it's probably, I mean, those are very simple experiments. I think the real issue, that sort of question is what do you mean by similar? That's the more complicated question.
Yeah, I mean, that is definitely a more philosophical question, I guess, like depends on what doctors want. But ultimately, if you think of this being used in a decision support system, let's say a doctor is trying to look at a current patient, and then if you can pull up like similar patients from the history and then say, okay, these patients had a similar trajectory, and then so they might be similar in risk or in like the treatment suggestions. That's one aspect of similarity that I'm thinking about.
Yeah, I'd argue if you're trying to estimate risk, you should just directly train a model to estimate risk.
Mhm.
And then you could just go by like these sorts of numbers to give you an estimate of how well these do for estimating risk. And if you're trying to estimate treatment effects, you should rely on these types of methods. You should just rely directly on doing actual observational studies, using Climber, and rely on these sorts of precision metrics to tell you how well that's going to work.
Yeah, I get what you're saying, but for instance, a model that predicts risk, if you had some amount of patient similarity, I feel like that can give some interpretability to why the model is giving a certain risk versus like otherwise it's harder to like completely trust the model when it says, okay, this patient is at risk versus not. And so you'll have to keep validating over time in order to make sure that that's actually accurate and holds when your data keeps changing as well.
Yeah, I agree with you. Well, yeah, there are huge, I'd say, customer usability benefits for like when you, in terms of talking about matched patients or finding similar patients compared to these sorts of like modeling approaches. I just don't know a good way to do that.
Yeah, definitely. Yeah, it's a big problem to think about, I guess. But yeah, I guess on that line, do you have any thoughts on how you can make this model more interpretable or explainable? Or are there some techniques that people can use to kind of get a sanity check on, okay, my model is predicting a certain amount of risk. I know why it's doing that.
I would say that's just about impossible to get anything that sort of looks, I'd say that's just about impossible because it's like trailed back through so many different, like the model seeing the entire patient, all the patients in the entire data set. You don't, it's hard to attribute any particular part of the risk score. I mean, you could try to do like local derivatives and stuff and use the standard interpretability stuff, but I don't think it'd give you that much of a value.
Got it. Okay.
I do think, well, this is sort of like a side aspect. I do think if you're interested in that sort of interpretability, what you should be doing is you should, the simplest thing you can do, or the simplest, most effective approach, is simply to remove ablate data from your patient and see how the predictions change with that ablated data.
I see. Okay.
And that's probably the most direct indication, or at least the easiest and most direct indication of what is driving the predictions. Especially because you can't do a simple derivative is probably not going to work for a deep neural network. So the direct ablation probably is the most straightforward approach, especially because for EHR data, the set of data for patients is pretty small. So you can actually, it's actually computationally feasible to ablate every code and do that ablation.
Got it. Okay. Any other questions? I guess if not, then let's thank Ethan again. We'll be putting up the YouTube video up tonight. And so you can always look back and if you have more questions, feel free to contact Ethan or feel free to contact us and we can put you in touch with him. Yeah, and I guess we'll see you next week. We are still yet to decide a speaker for next week, so we'll send out an announcement once it's done. But thank you all for joining today and we'll see you in future MedAI sessions. Thanks again, Ethan.
Thank you.
Thanks for organizing this.